Hi everyone! Today's topic is X-nary. You can do binary or quinary calculation quickly and correctly without changing it into decimal with expanded positional notation. Okay, let's get started. Hiding expo x. We can make it into X-nary as in video 17. When x is 5, it's in 5-nary notation, f of 5. Imagine this expression. There is a hidden expo 5. When x is 10, it's in tenary, actually g of 10. 212.3. Giving 10 to the upper place, 1 up minus 10. It's in decimal now. Tenary allows all numbers to occupy one place, while decimal only integers from 0 to 9. Giving 10 to the lower place, it's 310.13. In 5-nary, giving 5 to the upper place, 1 up minus 5 makes it in quinary. Quinary refuses 5 or more, allows integers from 0 to 4. Let me show you how carryover happens. It's an expression with x being 5. When dissolving this 7 into 5 and 2, since x is 5, this is 5 cubed. 1x cubed. So the x cubed's place is 3, and the x squared's place is 2. So you can give 5 to the upper place. Next example. In X-nary, when x is 7, it's a number in 7-nary, h of 7. Imagine this expression. In 7-nary, giving 7 to the lower place, 1 down 7, it's in septenary. It refuses negative number, allows integers from 0 to 6. I'll show you how 7 can goes down. Imagining this expression again. When dissolving 3 into 2 and 1, since x is 7, this is 7 squared, and 7 times 7. X squared's place is 2, and 5 is the x's place. This is 1 down 7. Move on to addition. It's in binary. Digit by digit addition. Binary refuses 2, so 1 up down 2. Once again, via decimal. Let's give expo 2 to make it in Nonary, like 4 times 1, 2 times 0, 1 times 1. Plus signs are omitted. Originally this. And so on. It's 5 plus 6. Then make it like this. In ternary. Then 11 has 5 2's. So carry over 5 to the x place. And 1 remains. From now, 11 divided by 2. Quotient 5, remainder 1. Then 5 over 2. Quotient 2, remainder 1. Then 2 over 2. Quotient 1, remainder 0. This is what you did before. Actually doing carryover with quotient and remainder. I made 11 as 4-digit, knowing x to the 4 is 5-digit in X-nary. 5 cubed, 4-digit. And 2 to the 4, 5-digit. 11 is smaller than 16. But usually, just place many zeros. Next example. Digit by digit addition. Quinary refuses 6. So 1 up, down 5. Don't make it in decimal, giving expo 5, unless asked to do so. It takes time. "91 divided by 5. 18 divided by 5. Move on to subtraction. Digit by digit subtraction. In ternary. This is 40 minus 6. So 1 down base 10. Like 1 down, giving 10, as in video 2. Once again, but nonary this time. Digit by digit subtraction. Then 1 down base 9. Like 1 down, giving base 9, 9 minus 6. Once again, Senary notation. Digit by digit subtraction. Also 1 down base 6. Like 1 down, negative 3. Giving base 6 minus 1. Then again, 1 down, giving 6. 6 minus 3. Then final 1 down, giving 6, It's done. But 3 times 1 down is troublesome, so let's use this. It's 9,990 in tenary. Call this all 910. Actually 10,000. Another all 910. All 9 plus 1. It's 1 million. How about 990 It's 1,000. Let's use all 910. This is a result of a subtraction. When negatives line up side by side, they get all 910. Like 1 down, giving all 910. Then 9 minus 3, 9 minus 2, 10 minus 1. In X-nary, all 5, 6 is like 10,000. 6 over 6, 6 over 6 again. In ternary, all 1, 2 is like 1 million. When consecutive negatives 1 down, all 5, 6, and the sum. We get the same result. Move on to digit change. Times 10 squared means 2 more 0. In X-nary, times x squared also means 2 more 0. This is what we did. X squared is 1x plus 0 squared. 1o squared is similar to decimal notation. In ternary, times 3 squared also means 2 more 0. It's just f of 3. Next example. Divided by 10 squared, the decimal point goes up by 2. In X-nary, divided by x squared makes the same. This is what happened. Also in Quaternary, divided by 4 squared makes the same. Substituting 4, we get f of 4. Move on to multiplication. A product in octal. Imagining this, 7 times 5, 7 times 4, 7 times 6. Then carry over 42 over 8, 33 over 8. It's done. Don't exponentiate it. For decimal, it takes time. Next example. When expanding it, we placed these product like this, as in video 17. In the same way, times 4 with 0, you can omit it, and times 3. Then carry over 10 over 5, 19 over 5. It's done. I'll do this again. When 7 is 8 minus 1, make it 1 negative 1. It's 8 minus 1. Then times 1 with 0, and times negative 1. Then the sum. One down, giving 8. I leave a hexadecimal equivalent. Just check it out. Next example. After this multiplication, the decimal point goes up by 2. This is what we did. Next example. Times 1 with double O, and times 1 with 0, as we did. And the sum. Then carry over. It's okay. But instead, let's use all 1 2. Here is all 1 2. It's like 10,000. And another all 1 2. And the rest. I'll show you another way. All 1 is all 1 2 minus 1. Then times 1 with 4 zeros, and times negative 1. 1 down, all 1 2. And the sum. Move on to transnotation from quaternary into binary. Inserting zeros between figures, it becomes in ternary. Then carry over 2 over 2, 3 over 2. It's done. The principle is simple. It's in Quaternary. and also can be X-nary. When x is 2, it becomes 4-nary. Next example. From nonary into ternary. Inserting zeros for 3-nary. 4/3, 7/3. It's done. Next example. From binary into quaternary. 1 down and base 2. Then remove zeros. Knowing 1-0 as 2 and 1-1, 2 plus 1. You can skip this line, seeing it as 2-digit by 2-digit. 3, 2. Next example. From octal to binary. Inserting double zero. It's in ternary now. Then carry over 6/2, 3/2, and so on. The principle is the same. It's in Quinary. Also can be in X-nary. Knowing 111 as 4 plus 2 plus 1. 7. And 100, only 4. You can skip this line, like 4 plus 2, 4 plus 1, only 2. In decimal binary transnotation, we need multiple divisions. To avoid mistakes, via octal over 8, 4 plus 2 plus 1, and only 1. Just give it a try. Move on to half-transnotation from 10-nary into 5-nary. This is the usual way. No problem. Instead, take only expo 2 out of 10 to exponentiate it. Then carry over, as we did. This is the principle. When x is 10, y is 5. Be sure to go to video 17. We did skeleting to make factorization easier. Next example. From 6-nary into 3-nary. This is via decimal. For comparison, I just leave an example. From hexadecimal into octal. This is from a college entrance exam in Japan. Here we go. Reduction in octal. Via ternary to binary. Then the binary point 2-digit left. Once again, 4 and 2, half and quarter, they represent each place. Next example, 100/9. In Nonary, 0.1, then in ternary, okay, let's move on to the drill. After this, be sure to go to video 1 and 17. You can apply X-nary for not only numbers, but also expressions. Okay, thank you for watching. See you next time. Bye!